Good afternoon, ladies and gentlemen. Thank you very much for joining our webinar this afternoon. To give you a basic idea of how this webinar will progress, I'm just going to introduce the major stages of this webinar. I will do a very short bit of introduction of our panelists and of our business. Trifona will then take us through the regulatory requirements in his presentation. This will be followed by another presentation from Yasmin, who will take us through some of the advanced concepts in evacuation. And then she will also take us through a demonstration of both Eve and Evie, our modeling product, as well as our evacuation analysis product. We will finish the webinar with a short presentation on alternative applications of pedestrian dynamics outside of direct evacuation. And we will conclude with a 10-minute Q&A session. In terms of the Q&A, this is how we would like to run it. There is a Q&A functionality within the Cisco WebEx. If you maximize your screen, at the top bar, there's a pull-down bar in where you can get pop-up windows for both the chat, and in the dot button, there is the Q&A pop-up. If you put the questions in the Q&A, they will come to us as panelists, and we'll either answer them immediately, and then both the question and the answer will be public to everyone in the meeting, or we will defer it to the Q&A session, at which point we will bring up the question and one of us will answer it verbally. Now, for a very quick introduction to the panelists, Vic or Victoria, myself. I've been in the maritime software business for about 20 years. Most of my career has been developing and selling a naval architecture product. And I joined Brookes Bell about 2 years ago to take some of our great products to market. Trifona has joined us 6 months ago and comes to us with over 20 years of experience in the maritime industry, both doing vessel designs as well as specifically system design and system assessment against safe return to port for clients. Yasmin joined us about 8 years ago after completing a MPhil in evacuation analysis, and she is our in-house expert for evacuation and our main user of our Evie product. Phil has been with the business for about 20 years, and he is our general IT guru, and he's here to ensure that everything works and we can deliver this webinar well. Just a very short introduction to our business now. Brookes Bell is a business of around 150 employees. We have global reach. We have 3 offices in the UK, but we also have offices in Singapore, Shanghai, and Hong Kong. We are a group of technical analysts and ex-seafarers. We provide consultancy in a whole host of technical subject matters, and we also provide expert legal advice. The business today that is our business is called Safety at Sea, and it is a subsidiary of Brookes Bell. And we have a number of software products, Evie, which is the subject of today's webinar, and you'll be seeing more of it today. And then we have 2 products focused on safe return to port. Systema, which is our system design tool that allows shipyards to analyze their system design against safe return to port regulations and create evidence for class. As well, our SRTP onboard tool is a tool for the crew to support them in managing the safe return to port response and also to prove compliance to flag. With that, I will now pass to my colleagues to start with the interesting presentations. Just give us a few seconds as we pass the ball and I hope you enjoy it.
Thank you, Vic. Our presentation consists of two parts. The first part is mainly introduction to the regulations and is presented by myself, and the second part referring to the advanced evacuation analysis and its application covered by my colleague Yasmin. The first part covers the regulations and more specifically the background of the evacuation regulatory framework development the last 30 years, where the regulations apply and what is the intention, the two available methods for evacuation analysis, scenarios and parameters to be considered, and finally the performance standard. Let's see how the regulations have been developed through time. The tragic event in 1990 of Scandinavian Star, where 159 people lost their lives, triggered a series of IMO EDRM guidelines to be published for new and existing passenger vessels, including high-speed crafts. The MSC 909, back in late 90s, introduced guidelines for simplified evacuation analysis, followed by MSC 1033 at early 2000s, setting the basis of the advanced evacuation analysis for new and existing vessels. Following the incident of Costa Concordia with 32 fatalities in 2012, new IMO regulations have been introduced in 2016 under MSC 1 Circular 1533 for new and existing vessels, making the evacuation analysis mandatory for passenger vessels built on or after 1st of January of 2020. In the following slide, we see where these regulations apply, what are the intention and assumptions made for the evacuation analysis. The regulations are mandatory for RoRo since 2002. What is new is that also they have become mandatory for all passenger vessels carrying more than 36 people built on or after 1st of January 2020. Their main intentions are evacuation duration estimation, identification and elimination of congestions along escape routes caused by passengers and crew movement, demonstration of escape routes flexibility when certain routes or life-saving appliances or even assembly embarkation stations are lost. Also, a proper analysis can identify areas of intense counter and cross flows and provide useful information to the operators. During the analysis, the following assumptions are made. Performance is based on standard scenarios and on an actual emergency. Passengers and crew load according to FSS code requirements. Orderly evacuation, together with no family or group behavior, are considered. The effect of smoke, heat, and toxic products, dynamic response of the vessel due to ship motion such as heel and trim. In the next couple of slides, we will talk about the differences between the simplified and advanced analysis. The simplified method is a manual spreadsheet exercise compared to the advanced computerized and automated method that is easy to update. The simplified analysis treats the escape routes as a hydraulic network, where the pipes are the corridors and stairways, the valves represent the doors and any other restrictions, and the tanks are the public spaces. The advanced method is based on the actual layout geometry and topology. The person's movement in the simplified analysis is represented as flow in the pipes, whereas in advanced method, each individual passenger is represented separately with distinct walking speed and reaction time based on the age, gender, physical conditions, etc. The reaction time is a fixed quantity in the simplified method, contrary to the advanced method using the probability distribution to estimate that time. Counterflow is one of the interactions between individuals. For example, when passengers are moving to master station while the crew moving towards the passenger cabins. If we use the hydraulic network analogy, counterflow can be described as the friction of the flow in the pipe. As per Annex 2 of the MSC 1 Circular 1533, a factor is used to account for the counterflow. The advanced analysis is taking place at granular or molecular level of this hypothetical hydraulic flow, where any passenger and crew member interact with each other. As we will see later in the presentation, these molecules are called agents. The congestion, a simplified method, is found by calculating the density of many escape routes on each deck, whereas the advanced method provides a quantification of density in all spaces and along all the escape routes. The simplified method is more suitable for simple layouts and can be used at the early design stage of a vessel. 2 decks and 2 main vertical zones would be the size for which the analysis is reasonable to do. There is no real limit to the size can be handled by the simplified method. However, it becomes more complex to define and perform the analysis while bigger the model gets. The advanced analysis can handle large and complex layouts of multi-deck arrangements, spreading across several zones. Let's move now to the scenarios and parameters part. There are 4 plus 2 new cases for the advanced analysis. They belong to 3 separate scenarios named as primary, secondary, and new. Each of the first 2 scenarios consists of a day and night case respectively. The escape arrangements are available in the primary scenario, whereas the stairway's capacity is reduced in the secondary scenario. The new cases apply where appropriate or as applicable. Cases 1 and 3 refer to the night configuration, where all the passengers resting in their cabins, with crew distributed in cabins, service, and emergency stations. For case 3, only the main vertical zone, which generates the longest individual assembly duration, taken from case 1, is to be considered. There are 2 options for investigating the selected main vertical zone. Either we assume that the staircase with the largest capacity is lost, or we add extra passenger load from the adjacent zone. Cases 2 and 4 refer to the day configuration, where 75% of the public spaces capacity is used by 100% of passengers, with crew distributed in public spaces, cabins, crew day spaces, service, and emergency stations. Case 4 is similar to case 3, but it uses the crew and passenger loading from the case 2. The 2 new cases apply as applicable to the ship layout and arrangement. Case 6 takes into account the travel duration from the assembly station to the entry point of life-saving appliance, if embarkation is separate from the assembly station. This is crucial to determine the embarkation and launching duration. Only 2 cases, night and day, are considered for the simplified analysis according to Annex 2 of the regulations. The following parameters are used for the advanced analysis. The first chart on left indicates that the walking speed for men and women is reduced with age. The response time is slower at night than day. This is reasonable considering that majority of passengers are expected to rest in their cabins. As we see from the age and gender distribution, the biggest group among passengers is over 50 years old, whereas the crew is considerably younger. There is an equal split between male and female population in passenger and crew distributions. Also, people with mobility impairment are included. The last slide of this part of the presentation is about the performance standard. Annex 1 of the regulations defines the maximum allowable evacuation duration for 3 passenger vessel types. The estimated time period, as described in the bar chart diagram, shall not exceed these limits. The same approach applies to simplified and advanced analysis. The indicated parameters in the diagram are as follows. R represents the response duration. For simplified method, 5 and 10 minutes are taken for a day and night case respectively. For the advanced analysis, this quantity is calculated based on a probability distribution, as we previously discussed. T is the travel duration as estimated by both methods. E and L represent the time needed for embarkation and launching. If no information or an estimate is available, we can use 30 minutes for the sum of these 2 parameters. As we can see in the bar chart, there's an overlap equals to 1/3 of the combined embarkation and launching duration. Therefore, the performance standard is defined as the sum of the response and travel time multiplied by a safety factor to account for the omissions, plus 2/3 of the combined embarkation and launching duration. This shall be less than 60 minutes for the first 2 vessel categories. For bigger passenger vessels, the limit is 80 minutes. Now I pass you over to Yasmin, who will go through the second part of our webinar about the advanced analysis and an avian example.
Thanks, Trifona. In the second part of the presentation, we will have a closer look at the advanced analysis and cover some practical aspects. We will be looking at the available modeling approach, then the verification and validation, which is an important part of the advanced analysis. We will also talk about the convergence criteria, which is a new addition to the guidelines, We'll move on to the benchmark scenarios that the guidelines suggest to perform and highlight some of the challenges, and finally conclude the presentation with an introduction to EVI. When it comes to advanced analysis, we need a computer program. The program is used to model the process by having a representation of the environment, the occupants, their movements, and interactions. The underlying phenomenon here is pedestrian dynamics. There are few tools available on the market, and we can broadly divide them into two groups based on the modeling approach that is taken: continuous and grid-based. Let's start with the grid-based approach. Models will use uniform grids to represent the ship layout, and each agent, which is the technical term for the representation of a person, will occupy a grid cell and can only move from one cell to a neighboring one, assuming the cell is free, that is, no other agent or obstacle are already there. This leads to simple collision avoidance and transitions, so overall the calculations are simplified. The main disadvantage of grid-based modeling is the accumulation of error due to the fixed grid size. There will be distortions to the model, either stretched or compressed. For example, if the grid cell is 0.5 meters and we have a door that is 0.7 meter wide, then either the door width is modeled by one grid cell, meaning we make it smaller, or by two grid cells and we make it bigger than it really is. Another thing that will be affected is the speed of motion. This is also dependent on the grid cell. The second approach is the continuous or semi-continuous modeling of space. This is a representation of the geometry that is closer to the reality. There is no restrictions in terms of where agent can be located, except the space already occupied by other agents. There are no restrictions either for the range and direction of motion, except for avoiding another agent or the geometry boundaries. This leads to more complex calculations, but with the computing power we have today, this is not challenging. One important aspect when using computer programs to solve any complex problem is to make sure that the program behaves as intended and provides the result as expected. To do that, we need to test the program. Without going into the details of software development, it is enough to know that there is a number of different tests we can perform. In the IMO guidelines, reference is made to the following tests. Component testing, we want to make sure that different parts of the software behave as intended. Qualitative verification, we are checking that the software can model the expected human behavior. Functional verification deals with checking that the software is doing what it is supposed to do. That means that we should see the software perform the expected functions. And finally, quantitative verification is when the outcome of the software is compared to real data. The IMO recognizes there is insufficient reliable data for thorough quantitative verification at this stage. So in the meantime, it is enough to test the software using the component testing, qualitative verification, and functional verification. Looking in more details to the component testing category, there are 7 benchmark tests. As I just mentioned, here we want to check that different parts of the software work as intended. For example, tests 1 to 3 check the correct walking speed can be maintained on flat and up and down the stairs. For the qualitative verification, there are 5 benchmark tests to check that the software can model the expected human behavior. The flow density test is a new test for this category, has been introduced in the 1533 circular, where the relationship between flow and density should be demonstrated. The expected outcome is that the flow should be smaller at very high population density when compared to the flow at moderate population density. But there is very limited information about this test in the guideline, except from the fact that the setup for the test should be a corridor without obstructions. A new addition to the guideline is the use of a convergence criteria. When we do an evacuation analysis, we cannot rely on the result of a single simulation, as a lot of parameters are characterized by probability distributions. So how can we tell if we have a good enough sample? Sometimes we can observe scattered results, which could mean that the number of runs might not have been enough to capture the variability for that particular scenario. Using a convergence criteria allows to define how many more runs we should perform to have a better sample. The previous guidelines recommended 50 simulation runs, 5 runs per 10 randomly generated populations for each scenario, But when doing a day case where there is a lot more variability, you would often find that at least 100 runs would be needed. The new guidelines now suggest using 100 different populations and do a total of 500 simulations. If there is enough variability, then the sample is good enough. If not, we start with a batch of 50 simulations, but this time the population is different each run. That is, we have 50 different populations. We checked for convergence. Appendix 3 of Annex 3 of the guidelines proposes one method to do that. If we have convergence, we stop. Otherwise, we do another 50 runs with another 50 different populations, and so on, up to a maximum of 500 runs. In the first part of the presentation, Trifona introduced the different scenarios to be modeled when performing an evacuation analysis. Here, in this second part, we'll be looking at the practical aspects when defining or modeling these scenarios and some of the challenges they may pose. One very important aspect to keep in mind is that we are not modeling emergency situations. Human behavior in emergency situations is extremely complex and very hard to model. Having said that, this does not mean that we cannot have realistic scenarios. The scenario can reflect the actual configuration in which the vessel operates. They can also be customized. If we are looking at a vessel without passengers cabin, for example, then a night case is not applicable. Another point worth mentioning here is that a percentage of the crew is not modeled, as they are assumed to be the emergency response team. This can be confusing sometimes when people look at the results of the analysis and don't see the full complement of passengers and crew. So starting with the night case, we saw earlier in the presentation that all passengers are in their cabins, 2/3 of the crew are also in cabins, and the rest is distributed between service spaces and muster stations. This is the easiest and most straightforward case and has very little variability in terms of starting locations, so usually there is no need to do a large number of simulations. For a day case, where passengers are in public spaces and crew are distributed between public spaces, cabin, crew service and muster stations, sometimes the layout of the vessel is such that it is quite easy to set up, but sometimes it can be a bit more challenging, especially if we think of cruise liners as they are getting bigger and bigger. Also, there is definitely more variability for case 2, so a high number of simulations would be expected. Another aspect of the day case is the validity of the crew going in counterflow towards the furthest cabins. This can be questioned here, as the movement of passengers would be completely different to a night case, and depending on how the people are assigned to muster stations, there might be a lot of counterflow already. Other things to bear in mind are the potential to adjust the scenarios in terms of routes that people take. So how do we assign people to muster stations? Is it totally random? Should we keep people in the same fire zone and only allow them to cross when they reach the muster station decks? What if we have already people in muster station? Should we keep them there? For the secondary cases, which have the same load as the corresponding primary cases, they can only be defined once case 1 and 2 have been simulated, as their definition depends on the results of the primary cases. So it is important to spend some time making sure that primary cases are correctly defined and simulated. For the secondary cases, the focus is on the fire zone that takes the longest to assemble, which is investigated further by either reducing the stairs capacity or adding to the load of the zone to be investigated. As with the primary cases, the secondary night case is usually straightforward to assess, but the secondary day might be more challenging. The next cases are case 5 and 6, and these are new additions to the guideline. Starting by case 5, the open deck case. This is to be investigated when the vessel to be analyzed has outfitted open deck to be used by passengers with at least 400 meters square, or is able to accommodate more than 200 people. This is mostly relevant for big vessels. The challenges here would be how to assign the muster station, because again, should we keep to the concept of staying in the same fire zone, even though in big open decks the limit of the fire zone is not that clear? And finally, case 6 is the embarkation case. This looks at the time it would take to travel from the muster station to the embarkation station if they were located at different places. There would be a need to closely work with the operator to be able to define this case, as very little guidance is provided in the guidelines, and at early design stages of the vessel, all procedures might not be defined. This concludes the presentation. But before we move on to the demonstration, I'd like to introduce Evie, our simulation tool. Evie is a software package consisting of an editor Eve and the simulation tool itself, Evie. Evie is a pedestrian dynamic simulation tool and has been first developed about 20 years ago. It has been used in consultancy work, R&D projects, and is used as part of the curriculum of some universities. Both Eve and Evie are very intuitive and easy to use. Now let's move on to the demonstration part. Right, let's start with Eve. I'm going to show you how you can quickly and easily build a simple model. This is a very basic layout inspired by the night case model of the IMO guidelines. The model we are building today has 3 decks and 1 fire zone, 1 main deck with the public spaces and 2 cabin decks. In this session, we'll be focusing on the cabin decks only. And in this example, we are using a GA to build the model. First, we need to name the database. This is not necessary, but it is good practice. We add the decks by clicking on this icon 3 times, as we need 3 decks. Then we set the height. Let's assume that there is a 3 meter difference between the decks. So we set deck 2 at 3 meters and deck 3 at 6 meters. The decks are then ordered by height. So we click on the GA icon to open a new window. If Eve uses files in the XF format, so we first import the GA of the main deck. The drawing needs to be scaled so they are in meters, and we also need to define the origin. This can be any point as long as it is consistent across all decks. We usually set the origin at frame 0. The origin and scaling can be done either in the CAD tool used to produce the DXF or here in Eve using the icon for the scaling and the setting of the origin. For this model, the origin was set here and the drawing has already been scaled. So once we are satisfied that the DXF is ready, we close the window, and on the panel here, we select the deck we want the DXF to be inserted to. Click here. We'll repeat the process for deck 2. And as deck 3 is identical to deck 2, we don't need to import another file. We just click on the insert GA icon. We can start now creating the geometry. Let's assume that we have a set of cabins here for passengers and here for crew. We can draw the first cabin. So we could choose to snap to the GA, and this is a feature that can be turned on and off, either in the preferences or at the bottom of the screen here. We can also choose to identify space by type. And once the cabin is drawn, we can use the array icon to quickly and easily draw the rest of the cabins like so. So we make sure that the space type is the correct one. And we do the same for the crew cabins. We can change the color of the space. Again, making sure that we have the right type. And we then set the capacity. So we select the cabins, set the capacity here to 2. So all cabins would have the same capacity. We do the same thing for the crew cabins. Now we need to create the corridors. So spaces in the model need to be convex, meaning if you have any 2 points in the space, if you draw a line between these 2 points, the line, must also be contained in the space. So we select here corridor. So we add 1 here. And in this particular area of the model, we would need more than 2 spaces, because if we were to select a point here and another one here, the line connecting them would not be contained within the space. So we need to add a corridor space, and then we connect them with union doors. These are not real doors, but they are a way to tell the software to consider this as a single space. So now we need to add the doors to connect the cabins to the corridor. There is an option in the software to automatically do that, but it's a personal preference of mine, just to add that manually. So adding that to the last few cabins. And then we need to add a corridor here. And another one here. And we connect them with those. Now we take advantage of the fact that the model is symmetrical, so we select all and then select the mirror icon, and we copy that across the axis. And then if we select the identification by type again, we see that the starboard part is now modeled. So we just finish off the deck by adding the missing corridor, and we connect that with union doors. And the fact that deck 2 and 3 are identical, we simply select all, copy the geometry, go to deck 3 and paste it there, and deck 3 is now modeled. The only thing left to do now is to add the stairs. We do have intermediate landing here, so we need to add a deck. We can rename it deck 2, 3, so we know it's between deck 2 and 3. We can also insert the GA here to help with the correct sizing of the landing. And if we assume that the deck is midway between deck 2 and 3, so we adjust the height and put it at 4.5 meters. So starting from deck 2, using the stairs icon, we draw the stairs. These are going up to deck 2, 3. We connect them to the landing on deck 2. We then tell the software which deck they're connected to. So we select deck connections to 3. We then go to deck 2, 3, and we can see that the stairs are here. We need to add a landing. And then connect the stairs to the landing with union doors. Then we need to model the stairs going up to deck 3. And again, we connect them to the landing, and then we tell the software where to connect that, and we select deck 3 in the deck connection. Finally, reaching deck 3, we see that the stairs are there, and the only thing left to do is to connect that to the landing on deck 3 using union doors. So now we can have a look at the model using the 3D view. And we can see here the cabins the stairs, and we can also open up the decks, have a closer look. And with this, we conclude the Eve part of the demonstration. And now let's move on to Evie. In this demonstration, we will be using a more complex model than what we saw earlier in Eve. This is a vessel which has 14 decks and 5 zones. When we do an evacuation analysis, what we want to know is whether the vessel meets the performance standard. So we are interested in the total evacuation time. And we also want to know if there is any congestion. So when we look at this example, the maximum allowable time would be 80 minutes, as we're having more than 3 main vertical zones. We first need to set up a scenario. So the scenario is defined by the initial location of the passengers and crew, the demographics, and the crew who starts in the different muster station and go in the opposite direction to the flow of passengers to create counterflow. Now that we already have the geometry, what we need to do is add the agent. There are different ways of adding agents for in Evie. So we can do that through commands or through a direct interaction with the model. But here we will be using the load case generator. This is very useful to define the agent distribution quickly and easily. The only thing we need to make sure of is that the space types are properly defined in the model. The load case generator comes with a preset for the night and the distribution of passengers and crew. So if we had a look at the day case, for example, we can see the breakdown of passengers and crew as of the definition of case 2 of the IMO guidelines, which we saw earlier in the presentation. So we have all passengers in public spaces, and the crew are distributed in public spaces, cabins, their day spaces, crew service spaces, as well as the muster station to go in counterflow. Here we could be easily changing the distribution. So if we were looking at an open deck, for example, what we could do is simply add that as a space type. So that would be for the case 5. And then all the crew and passengers who would normally be assigned to public spaces will also be distributed on the open decks. So for this example, we will be doing a night case. So now we just select night. And as you can see, the breakdown has now been updated. And for the night case, we already know that all passengers are in the cabins. Most of the crew are also in the cabins, and the remaining are distributed in the crew service spaces and the muster station to go in counterflow. So if we were to add the number of passengers and crew to this model, so we just do that. So now that we have all the passengers and crew added, we need to add the demographics. And that also comes with presets for both the day and night following the parameters of the IMO guidelines. For the age group and the probability distribution for reaction time and walking speed already defined. So now the only thing that remains to do is to instruct the crew to go to the crew who starts in the muster station to go to the furthest cabin. And to do that, we will be using commands. So I had prepared that in advance, and we only need to run these commands, and that will instruct the crew to go to the furthest cabin. So now we're ready, we've all set up, we just need to click run. But because this is a 90 case, nothing much happens in the first 400 seconds, which is the time it takes agent to wake up, realize what's happening, and start making their way out of their cabins. Because we're a little bit short on time, I had previously prepared or run a simulation. So in this case, that's exactly the same model and same setup. We can just go back to about 400 seconds, and that's where we will probably start seeing people moving. And then we can play from here, and as you can see, we start already to see movement. So we have the crew here, which are with yellow vests. They're making their way to the furthest cabin, and we're having the passengers making their way to their associated muster station. So here we can adjust the speed, and we can have a closer look at what is going on. So at any time, we can switch to the view, and we can also turn the density on, and we want to highlight areas of high density, which is more than 4 persons per meter square, and to see if we do have any significant congestion that is defined as more than 10% of, is defined as people being congested for more than 10% of the total time of the total simulation time. So we can turn off the agent and focus only on the density. And here, everything you see with highlighted with the diamond means that we have exceeded the threshold of 4 persons per meter square, and the redder it gets, the more people we have there, basically. In this model, Fire Zone 3, which is here, does not have any staircases, so agent will go towards the staircase of Fire Zone 4 to reach their muster station. And if we have a look at deck 10 in particular, we can see that this one has more cabins than the other cabin decks. So now if we were to go fast forward to the end of the simulation, we would see here, everything that's highlighted here in yellow is basically areas of significant congestion. So that would be an issue that we would need to basically look at for this particular model. The total evacuation time is here shown at the top. So for this specific run, it was more than 18 minutes. So going back to the congestion, one way we could possibly resolve that would be to split the load of Fire Zone 3 between Fire Zone 2 and 4. So we could instruct the passengers on deck 10, for example, to go both ways, and in Heavy we would be using the scripting to do that. So I had run a simulation where we have the split. So again, we can just use the playback to go to about 400 seconds, and we can focus here on deck 10. So as you can see, some agent will go towards Fire Zone 2 and some others will go towards Fire Zone 4. So we could even speed up a bit the process. And so there is still some high density. But then if we get to the end of the simulation, there's no more highlight of the spaces here. In terms of time, it's roughly the same time it took to get to the muster station, but we made some improvement in terms of congestion. Obviously, we cannot rely on the result of just one run to say, whether that may to make sure that this is the correct solution. So we would need to run multiple simulations to be confident in the results. One other thing we could be investigating in this specific situation is, instead of having the load split just for deck 10, we could be doing that for all the cabin decks. If we were looking at a design at an early design stage, one way to alleviate congestion would be to alter corridor widths, for example. So that would be one solution to that problem. So in terms of compliance, and to check whether the vessel meets the performance standard, as we said earlier, we need to have multiple runs so that we can be confident in the results that we have. We do that through the batch manager in Evi, and we can run multiple simulation with that. So I had prepared in advance a 100 simulation. I've run 100 simulation of the night case for the model that we see here on the screen. And the overall muster time is calculated taking the 95th percentile of all the arrival times. We add a safety factor to that, and we had assumed in this situation that we had 30 minutes for embarkation and launching, because we don't have any more data for that. So the performance standard in this situation would be roughly 44 minutes, and we would be well within the allowable time. To define the secondary cases, we would want to look at the fire zone that assembled last. So in this situation here, we had 100 runs, so 74% of the cases were indicating that fire zone 1 was the last to assemble, and the remaining 26 identified fire zone 3. So to do a night case, a secondary case, then we would investigate fire zone 1 further. And finally, quickly, the last page of the results show the exact location where the last agent to get to the muster station started from, and that is for only the first 50 runs. And with this, we end the EVI demonstration. One final thing before we move on to the Q&A session and end this webinar, we will briefly talk about other areas where we can use EVI. In our consultancy work in the past, we have used EVI to estimate the turnaround times at port. We looked at how long it would take to disembark all passengers, clean and prepare the vessel, and embark the next passengers. We made use of scripting capabilities to build the scenario, as this feature offers a lot of flexibility. The scripting is based on TCL. What you can see on the screen at the moment is a short clip of that turnaround study. EVI has also been used by one of our clients to assess escape and evacuation of the workforce during vessel building in a shipyard. They assessed, among other things, where to locate access points to allow for a timely, safe, and efficient evacuation. The diagram you can see on the slide is an example of a process to follow when we want to define an escape and evacuation plan. Another example of how we can use EVI is assessing the impact of route availability. If we decide to make changes to the way people access a specific area, like what is happening now during these extraordinary times, where we see one-way systems put in place almost everywhere, we can, for example, assess the impact local change could have on the overall dynamic of people's movements. This would be hard to foresee otherwise without the help of tools when complex layouts are concerned. To illustrate this with a very simple example, what you see on the left of the screen is a situation where all routes are available to people, and on the right, only a single route is available to them. We can see that the people reach the destination faster when they have access to all routes, but this creates congestion at the entrance of the destination. Whereas when only one route is available to them, they overall take longer to get there, but there is no congestion at the entrance anymore. Instead, the congestion is observed in the corridor where people start, and it takes longer to clear. So this would have an impact if more people were to join or use that corridor as part of their route. One final example of problem EVI could assist solving is crew procedures. We'll be looking at the muster list and SRTP drills. For people who might not be familiar, the muster list defines all the tasks crew are required to perform in case of emergency. Here, EVI could help in evaluating different what-if scenarios when defining, for example, the number and location of crew needed for a safe and orderly evacuation of passengers. For safe return to port situations, crew need to first contain the casualty, then restore a number of required systems, and this depending on the type of incident, by performing a set of manual actions. For that, they need to travel from different points in the vessel to the location of the equipment requiring manual action. Here again, EVI could help by evaluating, among other things, the different travel types. These were just few examples of how EVI could help. And with this, we conclude the presentation, and I pass you over to Vic.
Thank you very much, Yasmin. If you give me a second, I will share another presentation with some of the questions and answers that came up during this session. Give me 1 second, please. There we go. Okay, thank you. So, first question. How can this be used to justify either Regulation 17 or Regulation 38 challenges? I was going to pass this to Yasmin to answer.
Regarding the alternative design assessment, we can use EVI to, for example, estimate the required egress time and then compare it to the available egress time if we were looking at fire. If we were looking at LSA, for example, we could be looking at if we were having bigger lifeboats, for example, to have the logistics of how we could take people from the muster station to board the LSA. But we do also have done, well, we have done in the past consultancy work to assess alternative design. So that would be, if someone is interested, they can get in touch.
Okay, thank you. Next one. Could you explain the differences between the different door types and where we should use each one of them and how they affect the simulation?
So door types, we do have what we call real doors and artificial doors. So openings and union doors are there to connect spaces in the model, so that shows that it is a one continuous space. The opening has the characteristic that it is sizable, so we can adjust the size of that, whereas a union just connect the spaces through the whole length or width. Fire doors will be shown in the simulation as red doors, and they usually have fire bulkheads. And watertight doors will be again at watertight bulkheads. And we could set up the time to open, close doors, and go through these doors. So they would affect the simulation if we were to account for the time it takes to open, close, and go through the doors.
Thank you again. Okay, on our next question, can my E&L be more than 30 minutes if I have evidence?
The embarkation and launching is a maximum of 30 minutes as per SOLAS, so no, we won't be able to do that. But if we have evidence to show that it is less than that, then we could use that data in combination with the total evacuation time to the muster station, yes.
Okay. Should the congestion points identified manually for each simulation, how to evaluate the average presence of congestion in 500 simulations, like the total evacuation time?
So congestion points, well, there's a reporting command in EVI for all the results. So there's a lot of results we can get of the simulation, and one of them is the congestion. So we could use that command to identify the areas of whether there's congestion. So then post-process those results for the 500 simulations.
Thank you. How much computational time does a simulation take?
from few seconds to few minutes, and that depends obviously on the size of the model. So the bigger the model, the more agents you have, the longer it will take.
Thank you. Does anyone consider an escape onto shore, i.e. in port evacuation to quayside? So for this, it's not part of the regulation to do so, but certainly you can simulate it using EVI. You would have to model the shore side and a ramp from the ship to the shore side, and then you would be able to simulate the evacuation to the shore side. So I think this is the end of the general questions. There's one extra question coming in extra time, shall we say. If you don't make the required evacuation time, how do you improve on the evacuation time? What sort of design changes can you do? Yasmin, for you.
Sorry, can you say that again?
So if the simulation shows that you do not achieve the required total evacuation time, what sort of design changes can you look at to improve the situation?
Obviously, the first thing would be staircases, because that's where usually we notice the most congestion and issues. Also, possibly the width of doors, corridors. That's the kind of things you should be looking into. That could possibly alleviate that. The choice of routes, the location of your muster stations. That a lot of parameters that you could look into.
Okay, I think that gets us. Oh no, there is one more. Sorry. Is there any function to add passenger age groups and different walking speeds in the simulation?
Yes, you can customize that. So if you have data from trials or different data than what the IMO requires, then yes, you can customize that and adjust it to whatever you want, basically.
And that, thank you very much. That gets us to the end of this webinar. Thank you very much for all your questions, and I hope it's been useful and interesting. We have a further webinar next week on Safe Return to Port, the impact on operations, and we'll be demonstrating our SRTP on board software tool. If you should be able to register through the same link as you used to register to this webinar. If you have any issues, or if you have any further queries or any interest in the software, then please send us an email at software@brookesbell.com and we'll get back in touch with you. Thank you very much, and have a very good evening.
Bye.
Bye.